the universe. I mean, from the most distant galaxy you can possibly imagine, right down to the atoms making up your body. What if it's all been connected, like fundamentally linked since the very beginning? That's what we're diving into today, this really mind-bending idea, universal entanglement, and how it might trace all the way back to the Big Bang.
Exactly. And our mission, really, on this deep dive is to explore that question. Is the universe fundamentally connected, non-locally connected? We'll be looking at its quantum roots, the science, trying to figure this out, and maybe even trying to observe it. And all our discussion today, it's based on excerpts from Cosmic Genesis, Universal Entanglement from the Big Bang.
So yeah, get ready. It's going to be quite a trip through cosmology, through quantum mechanics, and I really think you'll have some moments where it just clicks, those aha moments. Okay, so let's start right at the beginning. The Big Bang model. This is the main scientific theory, right, for how everything got started. Around 13.8 billion years ago, the observable universe, everything we see, just emerged from the state of, well, unimaginable density and temperature. People often call it a singularity. But the key thing, and this is really interesting, it wasn't like an explosion in space. It was space itself appearing and time. So every single particle, all the energy, everything around you, including you, traces back to that one single unified event.
That's the core idea. Georges Lemaître, he pictured it as the universe expanding from a primeval atom. Now, link that to quantum mechanics, our best theory for the small stuff. A single isolated system. It's described by one big quantum wave function. Covers everything. So if the whole early universe was this primeval atom, well, it had to be described by a universal wave function, meaning it must have been entangled. It just had to be.
Oh.
So the real question isn't if it was entangled at the start. It's how did that initial whole quantum state, how did it evolve? How did it seemingly break apart into the separate things we see now?
Right. And that evolution, it was intense. Expansion, cooling, super fast. In those very first moments, just a scorching hot soup, quarks, gluons, fundamental stuff. Then, maybe just a few minutes later, Big Bang nucleosynthesis. It forged the first light atomic nuclei, mostly hydrogen and helium. And the amazing thing, the amounts it made, they perfectly match what we measure out there today. That really points to this shared creation event for all matter.
And we have solid evidence for this whole picture. It's not just a nice story. First, Edwin Hubble. He saw the universe is expanding. Hubble's law. Distant galaxies moving away faster the farther they are. Second, maybe even stronger evidence, the cosmic microwave background, the CMB.
The afterglow, right?
Exactly, the afterglow, this faint, uniform radiation everywhere. Found back in '64, it's like a relic heat from when the universe was about 380,000 years old. Cooled down enough for light to travel freely. And its uniformity is stunning. Almost perfectly smooth, just tiny temperature wiggles, 1 part in 100,000. That snapshot screams hot, dense, and very interconnected beginning.
Okay, so interconnected beginning established. Now let's zoom in on that connection itself. Quantum entanglement. This stuff is, well, it's weird. It really messes with our everyday intuition. You have particles that are linked so deeply you can't describe them separately. You need one single quantum state for the whole system. And here's the wild part. Even if you know everything possible about the system as a whole, you still don't know the state of each individual particle until you measure it. And they stay linked no matter how far apart they get. Measure one, and you instantly know something about the other one, instantly correlated. It seems like faster than light communication, even though it isn't really.
Right, and it's tied into superposition, another quantum weirdness. Before measurement, a particle is kind of in all its possible states at once. For an entangled pair, the whole system is in a superposition of all the correlated outcomes. Like spin up, spin down, and spin down, spin up at the same time. The outcome only gets fixed when you actually measure it. And this instant correlation across space, that's what Einstein, Podolsky, and Rosen hated. Their EPR paper in '35.
The spooky action at a distance.
That's the famous phrase, spooky action at a distance. It just felt wrong to them. It seemed to violate locality, this common sense idea that what happens here shouldn't instantly affect something way over there.
So for ages, the debate was, is this spooky link real, or is it just that the particles had hidden instructions from the start, local hidden variables?
Exactly. Like they secretly agreed beforehand how they behave. And that's where John Stuart Bell came in, 1964. Huge breakthrough. He figured out a mathematical way to test it, Bell's theorem. He showed, basically, if these local hidden variables existed, the experimental results would have to stay below a certain statistical limit.
Yeah.
Bell's inequality. But quantum mechanics predicted results above that limit. It predicted a violation.
And the experiments?
Overwhelmingly confirmed quantum mechanics. Starting in the 70s, experiment after experiment violated Bell's inequality. So quantum non-locality is not just theory. It's experimentally verified, it's real, but, and this is crucial, it doesn't let you send messages faster than light. The outcome of any single measurement is still random. You only see the spooky correlation when you compare the results from both ends later on.
Okay, so Big Bang origin, check. Entanglement and non-locality, check. But how does that little spooky connection get blown up to a cosmic scale? That takes us to cosmic inflation. You mentioned the Big Bang model is great, but it had some puzzles. Inflation was proposed to solve them.
Exactly. Inflation suggests this period of, well, almost violent exponential expansion. Right at the very beginning. We're talking a tiny, tiny fraction of the first second, like 1037 to 1035 seconds. And the universe just ballooned, grew by a factor of at least 1026. Maybe way more.
Wow, that's hard to even imagine.
It is. But this incredible stretching solves the horizon problem. It explains why the CMB is so smooth everywhere, even between patches of sky that seem too far apart to have ever exchanged heat or light in the standard Big Bang timeline. Inflation stretched regions that were initially close and in contact, smoothing everything out. And it solves the flatness problem, too. Why does the universe look geometrically flat, not curved? Inflation stretches out any initial curvature, just like blowing up a balloon makes its surface look flatter and flatter locally.
Okay, solves the problems. But you said there's a quantum connection here, the most profound part.
Yes. This is where it gets really deep. Quantum field theory tells us that even a perfect vacuum empty space isn't empty. It's this simmering sea of quantum fluctuations. Virtual particles popping into existence and vanishing again constantly. Tiny energy ripples.
Okay, like a subtle background noise.
Sort of. A fundamental quantum jitteriness. And during inflation, these microscopic quantum fluctuations in the vacuum energy field, they got stretched, massively stretched, to astronomical sizes. Tiny ripples smaller than an atom got magnified into the seeds of cosmic structure.
You mean the seeds for galaxies? And clusters of galaxies.
Precisely. Those initial quantum fluctuations, stretched by inflation, became the density variations, slightly denser spots, slightly less dense spots that gravity later pulled together to form all the large-scale structures we see, the cosmic web. So inflation acts like this incredible cosmic microscope. It makes quantum effects visible on the largest scales imaginable.
That's amazing. And you also mentioned particles popping out of the vacuum.
Yes, briefly. The immense energy of the expansion itself could be converted into particle-antiparticle pairs, actual matter from energy. It's something we can even replicate tiny versions of in labs, mimicking that expansion.
Okay.
And then, when inflation finally ended, all that energy stored in the expansion field, the inflaton field, it decayed. That decay reheated the universe, flooding it with a hot soup of particles and radiation we talked about earlier, the start of the hot Big Bang phase.
So thinking about entanglement again, these particle pairs created from the vacuum during inflation, were they independent or linked?
That's key. They had to be linked. Fundamental conservation laws demand it. Think about momentum or spin. If you create particles from nothing or from a state with zero total spin, the resulting particles have to have properties that cancel out. Like if a spin 0 particle decays into 2 spin 12 particles, their spins must be opposite, perfectly anti-correlated. That's an entangled state.
So particle creation itself creates entanglement.
Inherently, yes. For the cosmological perturbations, these quantum fluctuations, they are generated what physicists call two-mode squeeze states, which is just a technical way of saying they are intrinsically created in an entangled configuration, like cosmic dance partners born perfectly in step. So gravitational particle production is entanglement generation.
Okay, let's pull this together. What does this imply for this universal web of entanglement idea?
Well, it suggests something pretty profound. If all the matter, all the radiation, everything in the universe ultimately comes from that decaying inflaton field and this cascade of particle creation, and if that creation process inherently produces entangled pairs, then it means a fundamental non-local web of entanglement should underpin the entire cosmos, everything connected through this shared quantum origin.
So the giant structures we see, galaxies millions of light years apart,
They are, in a sense, the grown-up versions of those initial entangled quantum fluctuations, direct descendants. It's like a cosmic inheritance. The quantum correlations set up in the first tiny fraction of a second are passed down. So that galaxy way over there isn't truly separate from this one here. They're linked. By entanglement, that inflation blew up to cosmic scales.
Wow.
A deep, non-local connection woven right into the fabric of the universe.
Wow. Okay. That paints an incredible picture, almost mystical. But hang on, if everything's so connected, why does the world feel so separate? Why don't we see this spooky stuff constantly? Which brings us, I guess, to the big challenge. Quantum decoherence, this unraveling, as you called it. What is that exactly?
Decoherence is basically how the quantum world transitions into the classical world we experience.
Yeah.
It's a process where a quantum system, which might be in a superposition or entangled with something else, loses those distinct quantum features. It happens through interaction with its environment. Think of it like dropping a pebble in a perfectly still pond. You get nice clear ripples, right? That's coherence. But now imagine the pond is already choppy, full of waves. You drop the pebble, but its ripples immediately get lost, mixed up with all the other waves. That's kind of like decoherence. The system's quantum information leaks out into the environment it interacts with. The entanglement spreads out, gets shared with countless environmental particles, becoming incredibly diluted from any local perspective. So for us, looking at just a small part, the quantum weirdness seems to disappear. The system looks classical, probabilistic, like the wave function collapsed.
And the early universe was hardly a quiet pond, was it? Those primordial fluctuations were right in the thick of it.
Exactly. It was incredibly hot, dense, energetic. Intense interactions were happening constantly. Gravity especially played a huge role. Those fluctuations were interacting gravitationally with each other, with all the other quantum fields around. This constant interaction acted as a super powerful environment, driving decoherence extremely rapidly. For example, those big super horizon fluctuations we talked about, they decohered very efficiently by coupling gravitationally to smaller scale, unobserved fluctuations. Those smaller scales acted as the environment.
So decoherence doesn't actually destroy the entanglement.
No, not fundamentally. It just redistributes it,
Yeah.
scatters it. It gets spread across a practically infinite number of tiny entanglements with everything else in the universe. So the original pure state entanglement between, say, two specific regions that originated together becomes almost impossible for us to access locally. The universe evolves into this incredibly complex, mixed quantum state.
Mixed meaning. Scrambled.
Scrambled, yeah. From our perspective, the initial pure connection is hopelessly lost in the noise. The information is technically still there, encoded in global correlations across the entire universe. But we can't measure the whole universe. And that's essentially the quantum to classical transition in cosmology. That's why our world looks classical.
Okay, so decoherence explains the classical world, but could there still be some faint whispers left, some residual hints of that initial quantum state? Where are scientists actually looking for these relic signatures?
Well, the absolute prime hunting ground is the cosmic microwave background, that oldest light. Researchers are sifting through the CMB data looking for subtle statistical patterns that maybe, just maybe, don't fit the purely classical picture perfectly. One thing they look for is higher-order correlations, or sometimes called non-Gaussianity.
Non-Gaussianity, meaning not perfectly random.
It's exactly. Standard inflation predicts the initial fluctuations should be almost perfectly random, statistically like a bell curve Gaussian. But interactions, maybe stemming from that initial entangled state, could introduce slight deviations from perfect randomness. They look for specific shapes in these deviations, using tools called 3-point and 4-point correlation functions. Think of them as searching for specific, faint patterns in the CMB map. These could be fingerprints of the initial quantum state.
Okay, what else?
Another potential signature, much more exotic, involves parity-violating correlations. Some theories predict a very specific kind of correlation in the CMB that would be, well, asymmetric, directionally dependent in a spooky way. If found, that would be a real smoking gun for a quantum non-local origin, because classical physics doesn't usually produce that sort of thing on large scales.
Anything else?
There are also more theoretical measures, like quantum discord or mutual information. These try to quantify how much quantumness from the initial state might have survived decoherence and transferred into the patterns we can actually measure in the CMB. Calculations suggest these signals would be incredibly weak, especially on large scales, like trying to detect a single quantum whisper across cosmic distances. Extremely challenging.
Are they looking anywhere besides the CMB?
Yes, definitely. The primordial gravitational wave background, those faint ripples in space-time from the Big Bang itself, is another key target. The way these waves are polarized might hold clues about quantum effects or entanglement at their origin. Also, people look at the clustering of galaxies, the distribution of matter on large scales. And even more speculatively, things like primordial black holes, if they exist, or the origin of cosmic magnetic fields. Could they carry quantum imprints? It's all part of the search.
This sounds incredibly difficult, like searching for a needle in a cosmic haystack that's also on fire and flying away from you. What are the biggest roadblocks?
Huh, that's not a bad analogy. The hurdles are immense. Technically, the signals are expected to be incredibly faint, buried deep in noise from our instruments, our own galaxy, other galaxies. Just filtering that out is a massive task. Then there's a fundamental limit called cosmic variance. We only have one universe. So for the biggest features in the CMB, the largest scales, we literally have only one sample to measure. It's like trying to deduce the average height of humans by measuring only one person. Your statistics are terrible. It makes it really hard to tell if a weird pattern on a large scale is a real signal or just a fluke, random chance in our specific cosmic patch.
Right. One universe isn't great for statistics.
Not for the big picture stuff, no. And then there's a really deep conceptual problem. Classical correlations can mimic quantum ones. Decoherence itself smooths things out, but regions that started close together will still end up having similar properties just because they shared a common origin. That creates classical correlations that can look like entanglement if you're not careful. Distinguishing a genuine non-local quantum link from just a shared history is extremely tricky.
And what about measurement itself? You said entanglement is fragile.
Exactly. The fragility of entanglement is a huge issue. Any interaction can disturb it. And the very act of measuring a quantum system fundamentally changes it, the infamous wavefunction collapse. So it creates this almost philosophical catch-22. How do you even design an experiment to test non-local quantum correlations across the cosmos without your measurement setup inevitably collapsing the state and erasing the very quantum signature you're trying to find?
Yeah.
People are working on theoretical ideas for non-local measurements, but it's a major frontier.
This is starting to bend my brain again. There's also this philosophical issue, right? The freedom of choice loophole from lab tests. How does that play out cosmically?
Ah, yes. That's maybe the deepest problem of all. A proper Bell test, the kind that proves non-locality, relies on a crucial assumption. The person choosing what to measure, like which direction to measure spin, makes that choice freely and randomly, independent of the entangled particles themselves.
Yes, makes sense.
But in cosmology, think about it. Everything in the universe, the CMB light, our telescopes, us, the scientists making the choices, everything shares a common origin in that initial, potentially entangled Big Bang state. This opens the door to superdeterminism, the idea that everything, including our apparent free choices, was actually predetermined from the very beginning, fixed by the initial conditions.
Whoa, so my choice wasn't free. It was set 13.8 billion years ago.
That's the unsettling possibility superdeterminism raises. And if it's true, then any correlations we observe between distant parts of the universe wouldn't actually violate local realism in the way Bell's theorem assumes. Bell's theorem requires that measurement independence. If that's violated, the universe isn't necessarily spooky. It could just be playing out a script written at the dawn of time. It means we might be fundamentally unable to perform a truly loophole-free test of primordial entanglement because we are inescapably part of the system we're trying to measure. We can't step outside.
Okay, my head hurts a little. Let's shift gears maybe slightly to something almost equally mind-bending. This idea that space-time itself, maybe it's not fundamental, maybe it emerges from something deeper, something quantum, like entanglement.
Yes. This is a really exciting cutting-edge area in theoretical physics, a truly radical shift in perspective.
Yeah.
One key idea here is the ER-EPR conjecture, proposed by Juan Maldacena and Leonard Susskind. It basically suggests a deep equivalence between quantum entanglement, the EPR paradox spooky connection, and Einstein-Rosen bridges, which are, well, wormholes, tunnels through space-time.
Wait, entanglement equals wormhole, seriously?
In a mathematical sense, yes. It suggests that two entangled particles are somehow connected by a microscopic wormhole. It gives a geometric picture to entanglement. It's not just an abstract correlation, it's potentially a physical connection, a tiny space-time shortcut.
Okay, and how does the holographic principle fit in?
That adds another layer. Mark van Ramsdonk did some crucial theoretical work using holographic models. These are models where physics in a volume of space can be described by physics on its boundary surface. He showed mathematically that if you take two regions on the boundary and you cut the entanglement between them, the corresponding space-time in the bulk interior literally pinches off and splits apart.
Wow. So less entanglement means less connected space.
Or even no entanglement means no connection at all. His work strongly suggests that entanglement is like the thread that stitches space-time together. It's not just that entanglement happens in space. Entanglement might actually be creating the spatial connection itself, creating space.
That turns everything upside down. If entanglement builds space, what about gravity? Is gravity fundamental?
That's the next logical step. If space-time is emergent, maybe gravity is too. Maybe gravity isn't a fundamental force in the usual sense, but more like an emergent phenomenon. Something like thermodynamics arising from the collective behavior of underlying quantum information, specifically entanglement. Some research suggests you can actually derive Einstein's equations of gravity by considering entanglement, entropy, how much entanglement crosses a boundary. It implies space-time geometry, which is gravity and general relativity, responds to the flow and density of quantum information.
So the universe as a giant quantum computer and space-time is the hardware built from entanglement.
That's the ambitious vision, yes. Trying to unify gravity and quantum mechanics by saying gravity arises from the quantum entanglement structure of reality, space-time geometry encoded in this vast web of connections.
It's an amazing idea. Now, we spend a lot of time talking about inflation because it's the leading model. But for balance, it's not the only idea for the early universe, right? Are there viable alternatives?
Oh, absolutely. Science always explores alternatives. A couple of prominent ones are, first, bouncing cosmologies. These models suggest our universe didn't start from a singularity, but from the collapse of a previous cosmic era. It reached a minimum size, incredibly dense but not infinitely so, and then bounced into the expansion we see. The pre-bounce contracting phase can actually solve the horizon and flatness problems naturally without needing an inflationary period.
A bounce instead of a bang. Okay. What else?
Another intriguing idea, maybe more speculative, is the black hole universe. This suggests our entire observable universe might have formed from a gravitational collapse and subsequent quantum bounce that happened inside a black hole existing in a larger parent universe. Proponents argue this could explain things like dark energy and the universe's expansion using known physics, again, potentially avoiding the need for a specific inflating field.
Interesting. But even in these alternative scenarios, does the question of primordial entanglement still matter?
Yes, definitely. Because any plausible model that starts with some kind of ultra-dense, quantum-dominated phase and transitions into our classical universe is going to involve particle creation and intense interactions. And as we discussed, those processes naturally generate entanglement. So the core questions: was there initial entanglement? How much survived? How did decoherence play out? Can we see any remnants? Those remain relevant, regardless of whether it was inflation, a bounce, or something else that kicked things off. The quantum nature of the beginning seems inescapable.
Right. Which brings us back to a kind of practical critique. You hear physicists talk about Occam's razor, right? The simplest explanation.
Yeah.
How does that apply here to this idea of lingering, observable, universal entanglement?
That's a very important point. The standard model of cosmology called lambda CDM, which includes dark energy and dark matter, combined with a basic inflationary model and the known physics of decoherence. Well, it's incredibly successful. It fits the vast majority of our observations, like the CMB details, the distribution galaxies, the expansion history, with remarkable precision. So from a purely observational standpoint, invoking a currently observable, persistent network of cosmic entanglement isn't strictly necessary to explain the data we have right now.
It's like an extra layer of complexity we don't absolutely need.
You could argue that, yes. While the idea of a fundamentally entangled universe is philosophically fascinating and theoretically plausible based on quantum origins, adding it as an observable feature today lacks definitive proof. Occam's razor would suggest we stick with the simpler picture inflation, followed by near-complete decoherence leading to our classical universe, until there's compelling evidence demanding something more complex, like observable relic entanglement.
Okay, so let's try and bring this all home for everyone listening. This whole hypothesis, this idea that everything is entangled from the Big Bang, it seems to rest on pretty solid logic, right? A common origin implies connection, and then cosmic inflation gives us a powerful mechanism to take that initial quantum interconnectedness and amplify it, basically planting the seeds for all cosmic structure.
That's a good summary of the foundation, yes. But then the story of the universe's evolution is largely one of decoherence. This process acts almost like a cosmic curtain, hiding those deep primordial connections by spreading them incredibly thin, diffusing them across everything. And that's why our world looks classical, local, separated.
But the hunt is still on. This search, especially in the CMB for those incredibly faint leftover traces of quantum correlations, it feels like one of the ultimate frontiers, peeking back at the universe's very first moments.
It really is.
Yeah.
But we have to remember the immense difficulties. Cosmic variance only having one universe to look at. Classical effects that perfectly mimic quantum signals, the sheer fragility of entanglement, the fact that just looking can destroy the evidence.
And that deep, almost circular problem of superdeterminism where maybe even our questions were predetermined.
Exactly. Those are huge obstacles, both practical and philosophical.
So the big takeaway for you listening to this might be that the world you see, the world that feels solid, local, made of separate things, it might just be an effective description, a surface layer hiding a much deeper reality that's fundamentally non-local, interconnected, maybe even indivisibly whole.
And perhaps the most exciting thought to leave you with is this. As these ideas about space-time itself emerging from entanglement gain more ground, the question, how entangled is the universe, stops being just about matter and space. It becomes tangled up with the questions, what is space and what is gravity? They might all be different facets of the same deep quantum reality. And it makes you wonder, what discovery, what new theory or observation might finally let us read that oldest, most subtle message encoded in the cosmos? What's waiting just beyond our current understanding?